Hello, we're going to talk about representing functions as power series. So let's consider first the series sum from n equals 0 to infinity of x to the n. So notice this means 1 plus x squared plus x cubed, so on and so forth. Now we can interpret this for any fixed number x. We can interpret this as a geometric series. Well, if it's a geometric series, we know exactly when it converges. We know geometric series converge when the ratio, which in this case, the ratio would be x, converges only if the absolute value of x is less than 1. So based upon that, we also know what it converges to because it's a geometric series. We know that the sum of a geometric series should be the first term divided by 1 minus the ratio. And so this means that the sum, as n goes from 0 to infinity of x to the nth power, this 1 plus x squared, so on and so forth, this is equal to the first term of the series, 1, divided by 1 minus the ratio, which is x. This is a function, and when we happen to be in a situation where the absolute value of x is less than 1, the series converges. So we are saying that this function is the same as writing this power series when x is between -1 and 1. So in this way, we have said the function 1 over 1 minus x, I don't have to think of that as a division problem, but I've been able to rewrite it as a polynomial expression. And more so than that polynomial, if it's a positive value of x, I could use an integral test remainder estimate, or if it's a negative value of x, this will be an alternating series, so I could use the alternating series test, and I actually would be able to estimate how many terms of this series I might need to sum up. So what degree polynomial of this infinite polynomial I could sum up to get a decent estimate of the value of 1 divided by 1 minus x for a number in this area. Isn't that cool? Let's extend this and build estimates of other functions. Say the function that I want to look at is the function 1 over 1 minus x cubed. If I can interpret this left-hand side, if I can revision this left-hand side as the sum of a geometric series, then that's going to allow me to build a power series that will give the same value on the x values for which it converges. So that's the game we're going to play. So what would that be in this case? The thing playing the role of r here is x cubed. So the sum n equals 0 to infinity of x to the n gives me 1 over 1 minus x, so this is going to be the sum n equals 0 to infinity. I replace my x with x cubed to the n, or the sum n equals 0 to infinity of x to the 3n. Think about what we're talking about here. We're talking about the sum of 1 plus x cubed plus x to the 6th plus x to the 9th, so on and so forth. Here, now again, I can figure out, well, what would be the radius of convergence? So when is this true? This is true whenever the series converges, so it's going to be true when the absolute value of the ratio, so the absolute value of x cubed, is less than 1. Well, since when you cube a number, the cube root of 1 is 1, and cubes respect the plus or minus, this implies that the absolute value of x cubed would be less than 1, which implies that absolute x is less than 1. And so we are getting the same radius of convergence here from -1 to 1. When x is in the interval from -1 to 1. So the interval of convergence isn't quite what I'm using here. Notice that I'm using the fact that it's a geometric series, so I'm not going to check endpoints because the geometric series only converges on those values. All right, let's look at another one. Let's do this again. How about the function f of x equals 1 over 1 plus x squared? So remember, the game is I want to look at it as 1 over 1 minus some r. So what would my r here be? That's 1 over 1 minus a minus x squared. The double minus makes it a plus. And so what's playing the role of my r here is negative x squared. So when the absolute value of negative x squared is less than 1, the sum of this geometric type series can be rewritten as the sum, n equals 0 to infinity, of my ratio, which in this case is negative x squared raised to the nth power. Distributing that n power to to the parts of the expression negative x squared here, I'm going to rethink of this as negative 1 times x squared raised to the n, and so I can rewrite this as negative 1 to the n times x to the 2n. So if you will, what I'm saying here is that the function 1 over 1 plus x squared, which is a quotient function, rational function, can be rethought of as the infinite dimensional polynomial 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus x to the 10th plus so on. These two things are equal when the absolute value of negative x squared is less than 1, and this implies that x would be between negative 1 and 1 again. Let's try one further variant of this idea. Let's take this function g of x equals 1 over 1 minus 3x. Well, now the thing playing the role of my r is 3x. So we're going to say that this is the same as the sum, n equals 0 to infinity, of 3x to the nth power, or the sum n equals 0 to infinity of 3 to the n times x to the n, when that piece playing the role of the ratio, the absolute value of 3x, is less than 1, which implies that 3x is between negative 1 and 1, backwards order, 1 and negative 1, and therefore x only between negative a third and a third will we be able to obtain this estimate. But I do again here have a power series that plays the same role as this rational function. Let's make it even more interesting. What if I looked at this function, h of x equals x over 1 minus x? Now remember, this means I'm taking x times 1 over 1 minus x. What I'd like to do is see, is there a power series centered at 0 that could estimate the value, or that could give us the value of this function? So notice it's not giving it to us for all values of x, but for some it is. Well, if I can replace 1 over 1 minus x with this power series, n equals 0 to infinity of x to the n, then the function I'm talking about says take x and multiply it by this power series. Now, while that is an infinite sum, remember that if we're saying it converges between negative 1 and 1 in this case, so on the interval of convergence, then the sum part is giving me a number, and I'm just saying multiply it by x. But because it is a sum, I can use the distributive property, x times 1 plus x squared plus x cubed plus x to the 4th, so on and so forth. And therefore, I'm able to rewrite x over 1 minus x as, I'm going to distribute the x to each term, so that's 1 times x times x plus x cubed times x plus x to the 4th times x, or x to the 3rd times x, so on and so forth. So notice it's increased it, and this is now the sum, if you will, n equals 1 to infinity, or we could write it as n equals 0 to infinity of x to the n plus 1. So basically I can actually move the multiplication inside the sum of the series. This part here was really the sum of x times x to the n. So that's neat. I can multiply by powers of x. It also means I can multiply by constants. If instead I wanted to find the function f of x equals 8x over 1 minus x, and I wanted to write that as a power series centered at 0, at least on the interval of convergence, then I view this as being 8x times that series I had before. And since I know the series is convergent, once I've restricted myself to absolute x less than 1, then I can multiply inside the sum, so 0 to n of 8x to the n plus 1. And that becomes an infinite power series that represents the value here. So just to wrap up this example, I want to make sure we include the interval of convergence, or the values on which this holds. In this case it was negative 1 to 1, and in this case it was negative 1 to 1.